Hello, am I audible?
Yes, sir.
Gloria?
Yes, sir.
So let's start. Mechanical property of solids. To start with this part, let me define you one term. You must have learned about spring in chapter number 6 and work energy. Suppose there is support from which spring is connected, which having its natural length as L from this point to this point. Now, if you stretch it or compress it like this, so initially it was at this point, which will be termed as mean position. So on compressing it along this, and on stretching it, a force will develop into this particular spring, which will tend to regain its original shape. So for this part, force will be along this direction, and for this, force will be along this direction. A force which will tend to restore its original shape configuration is termed as restoring force. So this will be restoring force. And for this compression and this extension in this particular spring, which will tend to deform the shape of this particular body, so you call it as deforming force. Is it clear till this part?
Yes, sir.
Yes, sir.
So now, this particular spring has ability for this deformation while compression or extension. There is a force which get developed into it due to this two deformation, which will tend to bring back to its original shape. This tendency of spring is termed as elasticity. So first is elasticity. As like this spring, solid behaves like this. Suppose there is arrangement of atom in a particular crystal, let's say, whose each corner is occupied by any atom, and bond in between them behaves like spring-like arrangement. So if you apply any deforming force to any end, so it will deform like this to this point. Due to elastic behavior of this bond, which is behaving like spring, a force will develop into it, which will tend to bring back to its original shape or configuration. This tendency of body is termed as elasticity. Is it clear?
Yes, sir.
So elasticity is the tendency or property of a body due to which it will tend to regain its original shape on removal of deforming force. Now, there is another property opposite to this particular elasticity is plasticity. So you'll say the inability of a particular object so that they can't regain its original state or configuration on removal of deforming force. This is termed as plasticity. So plasticity is the inability of body so that they can't regain its original shape on removal of deforming force. Savannah, is it clear?
Yes, sir.
In general, the property of a body will lie in between elastic nature and plastic nature. There is no any object which is perfectly elastic or perfectly plastic. So you'll say property of body would lie in between elastic and plastic. Just write it down till this part. You all have written?
Sir, almost.
Gloria, just write it down. I will define you later.
Yes, sir, done.
Mohammed Umar, you have written?
Yes, sir.
Suppose you have a spring having natural length L. If you deform it while compression or extension, this particular spring having a tendency to regain its original shape back. So a force will develop into it, which is called a restoring force, which will tend to bring this particular spring back to its original state. The tendency of a spring by which this restoring force will develop into it to bring back to its original state is termed as elasticity. Similarly, for any solid which behaves like a spring-like structure, let's say for a crystal, particles are arranged at this particular corner. If a deforming force is applied to any one of its edge or side to deform along this direction, so this particular body will have a tendency to bring back to its original state. This property of body is termed as elasticity. Opposite of this particular elasticity is plasticity, which is the inability of body so that they can't regain its original shape on removal of deforming force. It is termed as plasticity. Is it clear?
Yes, sir.
Gloria, is it clear?
Yes, sir.
Now, since there is no any object which is perfectly elastic or perfectly plastic, so property of body will lie in between elastic or plastic. Okay?
Yes, sir.
You all have written?
Yes, sir.
Yes, sir.
So with this deforming force and restoring force, we may define different term. First is stress. Suppose there is a solid hang by any support and a deforming force is applied along this direction. To extend this particular rod slightly to this length. So this will be a deformation produced in this particular body due to this deforming force. So stress is basically the ratio of amount of deforming force applied on any object per unit area. So stress is the deforming force applied on a body per unit area. So stress equals to deforming force divided by area of contact. Unit of force is Newton and unit of area is meter square. So its SI unit is Newton per meter square. And it will be scalar behaving. So you will say it is scalar quantity. Now, due to this deformation or due to this application of deforming force on this object, there is some amount of deformation with respect to its original shape. Suppose actual length of rod is L and deformation produced is delta L. So we define another term which is strain. So strain is the ratio of deformation produced in body divided by the original shape or configuration of object. So strain is the ratio of deformation produced and original shape. So strain equals to deformed configuration or deformed shape divided by original shape. As unit of deformed shape and original shape will be same, so they will cancel out each other. So strain will be unitless quantity. Mohammed Umar, is it clear?
Yes, sir.
Savannah, any doubt?
No, sir.
Okay, just write it down. You all have written?
Yes, sir.
Gloria?
Just a minute.
Okay.
Done, sir.
Mohammed Umar, you have written?
So on the last one.
Okay.
Done, sir.
Okay. Now, there is relation between this stress applied and the amount of strain developed in this particular object, which was defined by Hooke or Robert Hooke. It will be termed as Hooke's law. It states if temperature is constant and within elastic limit, I will define you what do you mean by elastic limit. So if temperature is constant and within elastic limit, the amount of strain produced in a particular body will be directly proportional to amount of stress applied. The more you apply stress on an object, it will develop or cause more amount of deformation or strain. So it will be at constant temperature and within elastic limit. The amount of strain produced in a body is directly proportional to the applied stress. It means stress applied is directly proportional to strain produced. So if you replace this proportionality sign by any constant term, you will get stress equals to some constant E times strain. And if you rearrange it, you will get E equals to stress divided by strain. So this E is called modulus of elasticity, which defines elastic nature of solid or a body. It will depend upon temperature and nature of material, but independent of dimension. So this modulus of elasticity will define you. It defines the elastic nature of body. It will depends upon temperature, nature of material, but it will be independent of dimension. Is it clear?
Yes, sir.
Muhammad Umar, any doubt?
No, sir.
Okay. Now, the next thing is, since stress is directly proportional to strain, so if you draw a graph related to these two terms, you'll get straight line like this, where this will be stress and this will be corresponding strain. So E is stress divided by strain, which is, according to this graph, will be slope. So you'll say slope of stress strain curve will define you modulus of elasticity. Suppose this line is inclined at some angle theta, so tan theta equals to E. Is it clear? Savannah, is it clear?
Yes, sir.
Okay, just write it down. You all have written?
Yes, sir.
Wait a minute.
Atif, will you please join after half an hour?
Yes, sir.
Reba,
Yes, sir.
just join after 30 minutes.
Okay, sir.
Yusuf,
Yes, sir.
join after 30 minutes.
Okay, sir.
Okay. You all have written?
Yes, sir.
Okay. Mohammed Umar, done?
Yes.
Now, depending upon these three terms, we may define different types. First is, suppose there is a solid like this, and force is applied along this direction or along this direction. So in this first case, this deforming force will tend to elongate this solid. So it will be termed as longitudinal or tensile. And if you apply this particular compression, so it will compress or tend to compress this particular solid. So it will be termed as compressile. So first is longitudinal or tensile stress or compressile stress. They will be differ only in direction, but in terms of magnitude, they will be same. So longitudinal stress equals to force or deforming force per unit area. Corresponding change in this particular solid would be along this direction in length. So it will be delta L with respect to its original length, that is L. Similarly, in this part, it will be till this delta L with respect to its original, that is L. So it will be termed as longitudinal strain, which is equals to amount of deformation with respect to its original shape. Now, the third is about Hooke's law or modulus of elasticity. So in this longitudinal or compressile, it will be termed as Young's modulus. So Young's modulus equals to longitudinal stress divided by longitudinal strain, or if you put all the values, you will get y equals to F into L divided by A times delta L. Is it clear?
Yes, sir.
Gloria, any doubt? Abhinav, Nida, Umar, you may continue or join in just 20 minutes. I will continue with your own original batch. Okay, Umar? Gloria, any doubt till this part?
Sir,
Yes.
isn't it supposed to be delta L in the denominator?
Yes.
Yes, sir, done.
Mohammed Umar, you have written?
Yes, sir.
This Young's modulus, since it is defined along longitudinal, tensile, or compressile, will define you elasticity in length. Since it is equals to longitudinal stress and longitudinal strain. So longitudinal strain is unitless quantity. So its SI unit will be Newton per meter square. Is it clear?
Yes, sir.
Gloria, you have completed till this? Next is, suppose you have cube or cuboid like this. In which base is kept fixed. Let this particular surface to be fixed. And now a horizontal force is applied on its top surface. So it will slightly deform like this. So deforming force would applied along this direction, tangential to this surface. So this will be tangential force to this particular surface, due to which this side will get slightly shift along this direction by amount x. This will be length L. So this deformation will be theta. This is called shear or tangential. So we define three terms related to this also. First is shear stress, amount of deforming force along tangential direction per unit area. Correspondingly, deformation developed is shear strain. So it will be just theta, which is equals to x divided by L. Now, if you take the ratio of these two terms in this shear part, it will define shear modulus, which will be equals to shear stress divided by shear strain. It will denoted by G equals to shear stresses F tangential divided by area into theta, or it will be F divided by A x by L. Now this will again having same unit as Newton per meter squared. And since due to this particular application of tangential force, there is change in its shape. So this shear modulus will define you elasticity in shape. Savannah, is it clear?
Yes, sir.
Gloria, any doubt? Mohammed Amir?
No.
Okay.
So for shear strain, what does X stand for?
X is amount of deformation or shift in this particular solid from its actual configuration.
And L is the...
Actual length of side.
Okay.
A is area of cross section of this particular surface on which tangential force is acting.
Yes, sir, done.
Mohammed Umer, you have written?
No, good, sir.
Okay. And third type of this particular stress is volumetric, which may be also termed as hydraulic. Suppose you have a solid sphere like this. And if a deforming force is applied from its all side, along this side, or along this side. So this deforming force will be perpendicular to tangent drawn at this particular point. So it will be termed as force perpendicular to this area of cross section, which is also termed as pressure. Due to this application of pressure, there is change in volume of this particular object. So we may define first volumetric stress, which is equals to force per unit area, and this force is perpendicular to this area. So we may call it as pressure or change in pressure. Corresponding deformation will be volumetric strain. So it will be delta V divided by V. As initial volume of this sphere is larger as compared to its final volume, so there will be negative sign in this part. And if we divide these two terms, it will define bulk modulus. So it should be equals to volumetric stress divided by volumetric strain. Bulk modulus is denoted by beta and should be equals to pressure divided by delta V by V with negative sign, or it will be minus of P into V divided by V. Is it clear?
Yes, sir.
Now in this part, for volumetric or hydraulic, it will define compressibility or rigidity of this particular solid. So beta will define compressibility of body. Again, its SI unit will be Newton per meter square. Just write it down till this part.
Yes, sir. Done.
P is pressure, which is force per unit area or perpendicular force per unit area. Mohammed Umar, you have written?
Yes.
Okay. Now, depending upon these terms, there will be a question to define for perfectly rigid body. For perfectly rigid body, there will be no change in its configuration. So delta L, delta V, X, these terms will be 0. Now, if you put these values, let's say for Young's modulus, it was F times L divided by A times delta L. So this delta L equals to 0. So 1 upon 0 will be infinity, which means Young's modulus, bulk modulus, shear modulus will be infinite for perfectly rigid body. Is it clear, Savannah?
Yes, sir.
Okay, just write it down.
So can you repeat the infinite part?
Okay. Since for perfectly rigid body, there will be no deformation along its length, volume, or any dimension. So change in length, change in volume will be 0. So if you put the value of delta L for this Young's modulus to be 0 to this part, it will be 1 over 0 or 0 multiplied with this A, it will be 0. So you're left with 1 or this term divided by 0. So 1 divided by 0 will be infinite. Similarly, beta, which was P V divided by delta V with negative sign. So this particular term will be 0. So any number divided by 0 will be infinite. So you'll get Young's modulus, shear modulus, bulk modulus to be infinite.
Okay, sir.
Mohammed Umar, you have written?
Yes, sir.
Savannah, do you have any doubt till this part?
No, sir.
Okay, so let's stop here for just 5 minutes. I'm continuing the rest of the whole student. Okay. Okay, let's start. We have already defined three different terms about stress, strain, and Young's modulus or Hooke's law. Do you have any doubt from last class, Abhinav?
No doubt, sir.
Okay. Since your second term will be subjective, so there will be some subjective question related to this, in which first, which one will be more elastic? For first, steel and rubber. Second, water and gas. So how to approach, how to solve these type of problem? You have to solve them mathematically. Let me define you. You'll say, take a bar of steel and rubber of equal length from any support. Let's say this, a rubber, and another one, steel, having same length and having same area of cross section. This is rubber, and let's say this is steel. And now if you apply same amount of deforming force on either one of them, for this F and for this F, Savannah, just tell me in which of the case you will get more amount of deformation, in rubber or steel?
Rubber.
Good. So in rubber, you'll get more amount of deformation. Let's say it will be till this part. Deformation in rubber, and steel, you'll get only this amount of deformation, delta L. Now to define elastic behavior, we have to define modulus of velocity. Since it is in terms of length, so we define Young's modulus. So as we had formula, y equals to F times L divided by A times delta L. F is same, length is same, area of cross section is same. So you'll say Young's modulus is inversely proportional to amount of deformation produced. So in this part, since deformation in rubber is very, very large as compared to deformation in steel, so Young's modulus of steel will be greater than Young's modulus of rubber. Hence, steel will be more elastic. Is it clear?
Yes, sir.
Riba, any doubt?
No, sir.
Okay, just write it down. You all have written? Atif, is it clear?
Yes, sir.
Okay. Yusuf, you have written?
Yes, sir.
Okay. Similarly, to prove the second term, that is in water and gas, since they are fluid, so just take a constant volume of them. So you'll say, take constant volume of water and gas in a balloon like this. So this will be water. And this will be any gas. Now, if you apply same pressure on both of them, so in which case you will get more amount of deformation in water or in gas?
Yes.
So the more amount of deformation will be in gas, it means its modulus of elasticity, that is in terms of volumetric stress, it will be bulk modulus. So bulk modulus of water will be more as compared to gas. So water will be more elastic as compared to gas. Is it clear?
Yes, sir.
Yes, sir.
Okay. So you may prove this particular term like this. Mohammed Umar, any doubt till this part?
No.
Okay. You all have written? Now, the next important part of this chapter is to define stress strain curve. Suppose there is a rod which is hang from any support and force or load is applying on it. So it will be longitudinal stress, and this x-axis will be corresponding amount of strain developed. So if you apply constant force on this particular rod initially, it will behave to go like this. Means strain and stress will be proportional to each other for some finite distance. Let's say A. So up to which stress and a strain is proportional to each other, it will be applicable by Hooke's law. Is it clear? Now, if you remove deforming force at this state, this body will acquire its original shape exactly. So it will exactly return back to its original state O. Is it clear?
Sir, can you repeat?
In this part, since if you apply deforming force on any solid, so initially stress and strain will be directly proportional up to this point A. And if you remove deforming force at this particular state A, body will have ability to regain its shape exactly as it was previous. Okay.
Okay, sir.
Savannah, is it clear?
Yes, sir.
Now, if you extend this particular solid a little bit more, let's say to this point B, and now deforming force is removed. So it will again have ability to regain its shape, but with some amount of permanent deformation from this point to this point, which is termed as permanent set. And it would be about 1 to 2% of its total length. It means up to point B, object have tendency to return back to its original state, but from A to B, it will have small amount of permanent deformation with it. Is it clear?
Yes, sir.
So this particular point B, up to which body has property of elasticity, is termed as yield point. Now, if you further apply stress to this particular object from B onward, it will move like this to reach at this some final point C. Now, in this region, if you remove deforming force, body will have lost their ability of returning back to its original state, that is elastic behavior. Means from B to C, there is no elastic behavior of body, so it will be termed as plastic nature, or it will be in plastic region. Is it clear? Abhinav?
Yes, sir.
Yes, sir.
This particular point C will be the maximum amount of stress withheld by that particular solid. So it will be termed as ultimate stress. And now, if you further apply stress to this particular object, now it will start flowing like this, and at any contradiction, it will break out at some point D. So from C to D, object will have tendency to flow, and at this point D, it will be termed as breaking point. Riba, is it clear? Nida, any doubt?
No, sir.
Sir, what will happen from C to D?
Object will start flowing. So it will be like this, jelly-like structure. And at any contradiction, let's say at this point, it will break. Okay.
Okay, sir.
Okay, just draw it. I will define you each term. You all have completed till this part.
No, sir. I'm not.
Okay.
Done, sir.
Mohammed Umar, you have written?
Yes.
Since in this part, I'm just elongating this particular object, so there will be longitudinal stress. But if you apply it, or if you apply compressile stress, so graph will be along this direction. So it will move like this from this point to this point, B, then C, and at some point D, it will get fractured. There will be similar curve in this direction also. Now let me define you from O to A. If deforming force is removed, then body will acquire its original shape exactly. So up to this point, Hooke's law will be applicable. Hooke's law will be valid till E. Now next is from A to B, if deforming force is removed, body will still have elastic behavior, but with some permanent deformation. With it. So this B point is termed as yield point, up to which the body has elastic behavior. Next is from B to C. Object will acquire object will have acquire plastic behavior. There will be no elasticity. In region from C to D, on small applied stress, object will tend to flow and get broken at any contradiction.
So for BC, is it there will be no elasticity, or is it there will be elasticity?
Just 1 minute. From B to C, since body has acquired plastic behavior or plastic nature, so there will be no elasticity. What I have written? There will be no elasticity. Is it clear to all of you?
Yes, sir.
Mohammed Umar?
Yes.
Okay. Rishan, is it clear? You all have written?
Yes,
Yusuf?
sir.
Yes,
Okay.
sir.
No, sir. Wait. Wait.
Okay. Muhammad Umar, you have written?
Yes.
Okay. Similarly, for this particular compression, we may define this will be A, this will be B, this will be C, and this will be D. But in this part, from B to C, or which is plastic region, from C to D, it will be tending to flow, and at this particular point D, it will get through. So it will be termed as fracture point. This particular B to C is termed as crushing region. So you may define two different terms related to this particular graph. You must have learned in your earlier class about two properties. First is ductility. Second is malleability. Third is brittle nature. Savannah, do you know these things?
Yes, sir.
Tell me about ductility.
The property of metals where they can be like turned into wires, and they can be twisted into wires, or I don't know.
Okay, next is malleability.
The property of metals where they can be beaten into sheets.
And what about brittle nature?
They break easily.
Okay, so ductility is mainly the property of body to be drawn into thin wires on beating. So it will be to be drawn into thin wires on beating. Next, malleability, to be drawn into thin sheets like foil on beating. And brittle substance, the substance which get broken into small fragments on application of very small amount of force. So it will be to be broken into pieces on beating. So on the basis of stress strain curve, the more you have plastic region or limit, it will have more ductility property, more malleability property, and lesser brittle nature. So this ductility, malleability, and brittle nature mainly depend upon plastic region of that particular graph. So ductility, malleability of a substance will be directly proportional to plastic region. The longer the plastic region of a particular substance be, it will have greater the property of ductility and malleability. And for brittle nature, it will be inversely proportional to plastic region. Is it clear to all of you?
Yes, sir.
So you will be asked by defining any graph in which one will have smaller plastic region and the other will have larger plastic region. And then you will be asked to define which of these two will have more ductility, malleability, and brittle nature. So you may define those properties related to this particular relation. Nida, is it clear?
Yes.
Okay. Rishan, do you have doubt? Okay. You all have written?
Yes, sir.
Atif?
Yes.
Okay. Mohammad Umar, you have written?
Yes.
Okay. Suppose there is two different curves. First is like this for substance A. And the other is for another substance B. So you'll be asked, which is more elastic? And next is more brittle. Okay, Mohammad Umar. Savannah, you can send answer in direct message to me. Riba, just tell me which one of these two terms more elastic or more brittle about A and B. Good, Savannah. Atif, just send your answer.
Yes, sir.
Good, Yusuf. Muhammad Umar, your answer is correct, but reason is wrong. Good, Atif. In last class, I had defined you about elasticity. Slope of stress strain curve, that is for longitudinal, it will define you Young's modulus. For two-dimensional, it will define you shear modulus. And for three-dimensional, it will define you bulk modulus. So this particular slope, that is for this part and this part. This slope of stress strain curve will define you about elasticity. So E, that is modulus of velocity, equals to slope of stress strain curve. So in this part, A have larger slope as compared to B. So you will say A is more elastic. And next for brittle nature, we just measure the plastic region of those terms. So plastic region mainly start with this part. So it will be longer for A, and for B, it is just up to this point, shorter for B. So the larger the plastic region, it will have more ductility, more malleability, and small brittle nature. So for B part, it will be more brittle. Is it clear?
Yes, sir.
Muhammad Umar, is it clear?
Yes.
Okay. Now the next term is the only derivation of this particular chapter is potential energy stored in a wire. Suppose you have a wire or a rod hang from any support like this. And a deforming force is applied at its end. Length of this particular rod is L. Area of cross section is A. Now, on applying deforming force to this particular point along this direction, it will get deformed to this length like this. But it will be in step. So initially it will be from this point to this point, then from this point, and then to this point. It will be in step, or deformation in this particular wire will be in step. So let's say this last deformation is dy, and the rest of the part from this point to this point is y, so that total deformation produced is small l. Is it clear?
Yes, sir.
Muhammad Amir, do you have any doubt why I've taken like this?
So can you repeat?
Okay. Suppose you have a wire having length capital L, in which on application of this deforming force F, total elongation produced is this small l. Now, since this deformation may have acquired in this particular wire in step, let's say initially it was from this point to this point, then from this point to this point, then from this point to this point. So I have taken this last strip to be dy, and rest of the term from this point to this point is y. Since this total deformation in this wire has not got the term exactly at one instant. It must be slow process of this whole for a particular finite time. Is it clear?
Yes, sir.
Okay. Consider a wire having length L, area A. A deforming force F is applied to deform it to L. At any instant, deformation is y, and small deformation is dy. So there should be some amount of work done to this particular wire to deform it by dy. So you may write it like this. As we know, Young's modulus is equals to stress divided by strain, or longitudinal stress by longitudinal strain. So F divided by A, delta L divided by L. So in this part, delta L is Y and its original length is L. So if you calculate force, it will be Y times A divided by L into Y. Is it clear?
Yes, sir.
Muhammad Yusuf, is it clear?
Yes, sir.
Savannah, any doubt?
No, sir.
Okay. Now, since total deformation in this wire is up to this particular L, but this must be achieved in stepwise. So at any instant, I have taken the deformation in this wire to be y, and to further deform it by dy, you must have to apply some amount of work on it by this particular force F. That force or that work done on this particular wire will get stored in the form of energy that is called potential energy. So let's say dW amount of work is done to stretch it by dy. So work done equals to force times displacement. Since this term is very small, so if you have to take complete part, so just integrate it. This work done on the spire, which convert into potential energy, so it will be denoted by U. Force is YA divided by L into Y dy, in which Y is Young's modulus, A is area of cross section, and L is length. These all terms are constant, so keep it outside. Only Y is variable, so take it inside like this. Is it clear to all?
Yes.
This Y will extend from this initial or no deformation to this final, that is L. So limit of Y will be from 0 to L. You must have learned about integration in your last part. Whenever you have x to the power n times dx integration, it will be x to the power n plus 1 divided by n plus 1. So in this, we have y to the power 1. So on integrating, it will be ya divided by L times y to the power 1 plus 1, it will be 2 divided by 2, having limit from 0 to L. First, write it down till this part.
Yes, Sudan.
Muhammad Yusuf, you have written?
No, sir. 1 minute. Sir, can you show that diagram?
Okay. Rishan, any doubt till this part? Okay. Mohammed Umar, you have written?
Yes.
Now, on integrating, you will get this part. So just use these two terms as limit. So you'll get y(a) divided by 2 times of L. Y to be L, so you will get L square. And for lower limit, it will be just 0 square. So on simplifying, it will be half ya divided by L into L into L. This term will be nothing but force, and this L will be elongation produced in that. So it will be half into force into L, or half into force into extension, is equals to potential energy. And since this potential energy is in a wire, so it will be termed as mechanical potential energy. Is it clear to you all?
Yes, sir.
I have put the value of y to be L as their limit. Okay, Mohammed Amir? Using the concept of integration for definite part. Okay, the next is, so if you draw graph related to this force and extension, since it is in terms of product, so in terms of graph, it will be defined by area under force extension curve. Is it clear to all of you? Atif?
Yes, sir.
Okay. You all have written till this part?
Yes, sir.
We may transform this particular formula in terms of stress and strain. As you have potential energy equals to half into force into extension. So divide this whole part by volume and multiply it by volume. This fraction will not change. We may write it as half force. Volume will be area into length into volume. This force per unit area will be stress, and this particular ratio will be corresponding strain. So it will be half into stress into strain into volume. So this will be your potential energy mechanical stored in wire in terms of stress strain. Is it clear? Mohammed Umar, is it clear? Okay, just write it down. I'm giving you some problem related to this. You all have written?
Yes,
Yes.
sir.
In this part, I've done, I've just transformed this above formula, which was in terms of force and extension, in terms of stress and strain. So I've just multiplied by volume and divided by volume so that this fraction will remain same. As volume equals to area of cross section to length, so wire having area A and total length L, so these two terms on multiplication will give you volume. Now for this part, force divided by area will be stress. Deformed shape by original length will be termed as strain times volume. So this will be your another formula for potential energy stored in the wire. Now this may transform into some other as well using the concept of Young's modulus, which is equals to stress divided by strain. So you may write stress equals to Young's modulus times strain and put it in this part. You will get half times Young's modulus into strain square times volume, or you may write strain equals to stress divided by Young's modulus to get stress square divided by 2 times of Young's modulus into volume. So it will be depending upon the given problem in which relation it is given, and you have to use these formula to obtain potential energy stored in a wire. Riba, is it clear?
Yes, sir.
Atif, any doubt?
No, sir.
Okay. Just write it down. I'm giving you problems related to this.
So,
Yes,
till what time is this class?
just 20 minutes more.
Okay, sir.
You all have written?
Yes, sir.
A wire having dimension as 2 mm square cross 4 meter, whose Young's modulus is 2 into 10 raised to the power 11 Newton per meter square. A force of 40 kilonewton is applied. Find first stress. Second, potential energy stored. First, rewrite according to the given term in question. You have area of cross section as 2 mm square. So just convert it in terms of meter square. So it will be 2 into 10 raised power minus 6 meter square. Length of wire is 4 meter. Young's modulus is 2 into 10 raised power 11 Newton per meter square. And applied force is 40 kilonewton. So it will be 10 to the power 3 Newton. Or you may write it as 4 into 10 raised power 4 Newton. Just use these values to find stress and potential energy stored related to that. Try to solve. Muhammad Umar, just check your calculation. Good, Muhammad Umar. Good Atif. Good Yusuf. Savannah, just send your answer. Nida, Riba, send your answer. Mohammad Umar, let me check. Stress equals to deforming force applied per unit area. Force is 4 into 10 raised to power 4. Area of cross section is 2 into 10 raised to power minus 6. So it will be 2 into 10 raised to power 4 minus 6. So it will be plus 10 Newton per meter square. Next is amount of potential energy stored. U equals to half Young's modulus area divided by L into L square. You may use this formula. Next is half Young's modulus times stress square into volume. You may use this formula depending upon your choice. So let me use this one. Half Young's modulus is 2 into 10 raised to power 11. Stress is 2 into 10 raised to power 10 square I have written the wrong formula. Just 1 minute. In terms of stress, it will be stress square divided by 2y. So it will be stress square divided by y. Stress is 2 into 10 raised to power 10 whole square divided by Young's modulus, which is 2 into 10 raised to power 11 into volume, which is area into length. Area is 2 into 10 raised to power minus 6. Length is 4 meter. So on simplifying it, you will get 2 into 2, 4 into 10 raised to power 20 into 2 into 4 into 10 raised to power minus 6 in numerator divided by 2 into 2 into 10 raised to power 11. So this 2 and this 2 will cancel out with this 4. So 2 into 4, it will be 8. 10 raised to power 20 minus 6, it will be 14 minus 11, it will be 3 joule, or it will be 8 kilojoule. Is it clear?
Yes, sir.
Mohammad Umar, just check your calculation. Rishad, is it clear? Okay. You all have written?
Yes.
Savannah? Okay.
Yes. Sir.
Now there is some term related in this chapter. First is elastomer. You must have seen or used a thermocol for different project purpose. So if you compress thermocol at a particular level or a particular extent and release it, it will come to its original shape. But if you compress this furthermore, it will get break. Similarly, for a rubber band, if you stretch it up to a particular limit, it will stretch and then again it will return back. But beyond that, it will get broke. So a substance which having only elastic limit and beyond which it will get fractured or broken, it will be termed as elastomer. So the curve related to those terms will be like this. If you stretch it, it will go along this part to reach at this particular point. And on releasing the deforming force, it will return back along this path to acquire its original state. So this will be the maximum amount of deformation produced, or it will be termed as saturation point, beyond which it will get fractured. So this will be stress, and this will be corresponding strain. So elastomer is a substance which has only elastic limit and beyond which it will get fractured is termed as elastomer. The substance which has only elastic limit beyond which it will get fractured is called elastomer. These elastomer can be used to get shock absorber for different injury. That's why thermocol mainly used for transportation of different devices, just like computer, television, fridge, AC, and so on. So these elastomer mainly used as shock absorber. So you will say the greater the area of this particular curve, it will have tendency to absorb more amount of shock, or it will convert more amount of energy or dissipate more amount of energy. So it will be good shock absorber. Greater the area, greater the area of stress strain, Is it clear? Muhammad Umar? Atif? Any doubt?
Sorry, can you repeat that, sir?
Do you have any doubt till this part?
No, sir, no doubt.
Okay. You all have written?
Yes, sir.
1 minute, sir.
Yes, we're done.
Yusuf, you have written?
Yes, sir.
Next is, and the last part of this term is bending of beam. You'll be asked just formula of this part. Suppose there is a beam like this. Having length L, breadth B, and width D, on which a load is applied at its midpoint, due to which it gets slightly deformed along this to this part. So amount of deformation produced or bending produced, developed in this particular beam from this point to this point is represented by delta on application of some weight on it. Let's say W. So this delta will be equals to four times Young's modulus BD cube divided by WL cube. Like this. So delta will be dependent upon these terms like this. So you'll be asked how delta is depending over length, over breadth, over depth, Young's modulus, and weight. So you have to remember only this part. Is it clear?
Yes, sir.
Just write it down.
Done, sir.
You all have written?
Yes, sir.
So this is all about your whole, about this chapter. So just to stop here, from next class, we'll start new chapter that is mechanical properties of fluid. Okay?
Okay, sir.
Okay, sir.
So just revise this whole part and try to do more and more problems related to this. Then we'll start from next class. Do you have any doubt to any one of you from today's class?
No, sir.
So how will they ask this equation?
You have to remember only this particular equation. You don't have to define about its derivation. Okay?
So they'll ask us just to write the equation.
Yeah. Or relation of delta with these terms.
Oh,
How is delta is dependent on width, depth, breadth, length. You'll be asked like this.
yes, sir.
Okay then. Good night. Take care.
Thank you, sir. Have a good day.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Yes, Muhammad Umar. Just ask. Suppose you have a beam whose length, breadth, depth is LBD, on which a load having weight W is applied, due to which it's slightly deformed from its original shape by some amount delta from its midpoint. And how do you calculate this particular delta? I have just defined it.